As we peer into space, we wonder about the origins not just of the universe, but also of the many astronomical objects, galaxies, stars, planets, moons. In this lecture, the 34th of the series, we'll examine the nebular hypothesis. That's the idea that stars and planets form from the gravitational attraction of dust and gas in space. My outline is simple. First, we'll take a look at the many objects that litter our solar system. These objects include planets and moons, comets, asteroids, and much more. We'll see how space scientists have spent the last several centuries gathering information on the composition and the distribution and the dynamics of these objects. And it turns out that these data provide strong hints about the origin of our planetary system. After that, I'll review the nebular hypothesis, which was first proposed by the French mathematician Pierre-Simon Laplace. That was more than 200 years ago. We'll look at the likelihood of solar systems forming around other stars as well, and I'll conclude the lecture with the very unlikely story of the formation of Earth's moon. Before discussing the solar system and its origins, it's appropriate to review what we've learned about the origin of the universe itself. Now, three kinds of observations provide compelling evidence for the Big Bang origin of the universe. That was the sudden appearance of all matter, all energy in an instant about 14 billion years ago. The first piece of evidence was the universal expansion of galaxies. That was described by Edwin Hubble in the 1920s. And remember that Hubble observed that virtually all the galaxies are moving away from us and that more distant galaxies are moving away faster. And then there was the discovery of the cosmic microwave background radiation. That's the uniform microwave static coming from every corner of space. It was discovered by Arno Penzias and Robert Wilson in the 1960s. It's exactly what theorists predicted based on the leftover electromagnetic radiation after the Big Bang. And then there's the distribution of light elements, hydrogen, helium, lithium, and especially the ratio of hydrogen to its heavier isotope deuterium. That ratio is revealed in the composition of old stars, and it's finely tuned by the Big Bang model. So there's plenty of observational evidence for the Big Bang. Furthermore, the analysis of the rate that galaxies are moving away from us reveals that the universe is about 14 billion years old. We also saw that the estimates of the total visible mass of the universe suggest that the universe doesn't hold enough mass to reverse this expansion. Gravity is slowing down expansion, but it can't stop expansion completely. The universe may continue to expand forever unless a substantial source of dark matter is discovered. Now, from these insights, it's clear that the Big Bang filled the expanding universe with matter and energy. And almost immediately, within 500,000 years or so, gravity began to pull that matter into clumps that would become stars and galaxies and clusters of galaxies. Peering through our most powerful telescopes, we observe these extremely distant and therefore extremely ancient objects. Remember, when you observe an object that's 1 billion light years away, what you're seeing is an object as it actually was 1 billion years ago. So the bigger the telescope, the farther back into time that we can see. In fact, using the exceptional resolving power of the Hubble Space Telescope, astronomers have glimpsed back in time to the first 1 billion years of the universe. They observed galaxies more than 10 billion light years distance. That's back to within the first 10% of the age of the universe. But clearly, by that early time, the universe was already littered with countless galaxies, each with billions of stars. So star formation and galaxy formation happened pretty quickly. These observations of the early universe, you see, are critical to understanding the process by which stars and planets form today. The universe is more than 10 billion years old, but most stars we see are less than 5 billion years old. Stars live out their lives. They die at a prodigious rate. So we have to conclude that star formation processes continue unabated today. Indeed, our galaxy features vast regions that are relatively rich in dust and gas. Exploding supernova stars continue to add even more raw materials for the formation of new stars. And what's more, the shock wave from a supernova explosion can trigger new star formation by creating locally dense regions in a dust cloud. So supernovas contribute to new star formation in a couple of different ways. And that's the theme of this lecture. I'll show you how stars and planets form from such a dust cloud. First, we'll review some of the characteristics of objects that form our own solar system. These objects provide important clues to the mechanisms of their own origin. Now, so let's take a closer look at the solar system. The solar system includes all the objects that are gravitationally bound to the sun. And remember, the sun's just an ordinary star. So in trying to deduce the history of the solar system, we first have to collect observations about its physical and chemical characteristics. Here's a representation of the solar system. With the unaided eye, we can see 5 planets in addition to Earth. And with telescope, astronomers have discovered 3 more for a total of 9 planets. Now, the 4 innermost planets here are relatively small and rocky worlds. They include Mercury. That's a barren, desolate, baked world closest to the sun. And then Venus, that's shrouded in clouds of carbon dioxide. The 3rd planet from the sun is our own Earth. And then comes the red planet Mars. These 4 inner planets are called the terrestrial planets. Then the next 4 planets are called the gas giant planets. These planets are composed primarily of hydrogen gas. They're actually like miniature stars that never quite got large enough for nuclear fusion reactions to begin. These planets are first Jupiter, that's the 5th and the largest planet. It has that great red spot. The next is Saturn, which has the most magnificent rings. And beyond Saturn are Uranus and Neptune, both of which were discovered with telescopes. These 4 planets are sometimes called the Jovian planets. And then we have a 9th planet, Pluto. Actually, for 2 decades at the end of the 20th century, Pluto is actually the 8th planet. It's inside the orbit of Neptune for that brief period, but its average distance is farther from the sun. As we'll see, Pluto is an odd object. It's much smaller than the Jovian planets, and it appears to be rocky. Indeed, some astronomers argue that it's not really a planet at all, but that's another story. In addition to the planets, quite a number of other objects are gravitationally bound to the sun. To begin with, most of the planets have 1 or more moons, and moons are simply objects that are gravitationally bound in orbit around a planet. Of course, the most obvious moon is our own large moon, and with a good pair of binoculars, you can also see 4 moons in orbit around Jupiter. Those 4 moons were discovered by Galileo Galilei, so they're often called the Galilean moons. Galileo actually called them the Medicean planets in honor of his sometimes patron, Cosimo Medici II. These 4 moons have received a great deal of attention recently because they're so active and dynamic. The closest in-moon, Io, has actually got volcanoes, and the other 3 may have their own ice-covered oceans of water. Then there are also dozens of smaller moons around Jupiter and around Saturn and other planets. There's other stuff in orbit around planets too. All of the gas giant planets have rings, and these are made of relatively small particles. The rings are especially obvious for Saturn. You can see the rings with a good pair of binoculars. The rings are composed of countless particles ranging in size from sand grains to some particles that are maybe a few kilometers across. So it's sometimes hard to know where rings end and moons begin. And then in addition to planets, countless thousands of other objects orbit around the sun. Numerous asteroids fall into this category. Asteroids are rocky objects, usually irregular in shape, that range in size from small boulders to substantial masses that can be hundreds of kilometers across. Now, one way of distinguishing these chunks of rocks from planets is their shape. A sort of rule of thumb is that asteroids are too small for gravity to pull the object into a spherical form, like planets or the larger moons. Most asteroids, and that includes more than 10,000 named and documented ones, are found in the wide asteroid belt between Mars and Jupiter. Some astronomers have speculated that Jupiter is so large that it prevented the formation of a planet in that closer orbit. So you get all these planetary fragments instead. A growing number of asteroids have been found to have highly elliptical orbits that actually cross inside the path of the Earth. So these Earth-crossing asteroids are the subject of lots of study because they constitute a potential threat to human life. The chances of any one of these asteroids hitting the Earth is very, very small, but a major impact does occur every few millions of years. And the impact of a kilometer-sized rock, that's a modest-sized asteroid, could cause incredible destruction on Earth. For that very reason, Carl Sagan spent a lot of time during the last years of his life lobbying for a space monitoring system that would provide an early warning for any possible impact. And then there are the beautiful comets. Comets have been described as dirty snowballs in space. They're rich in water and methane and other volatile materials that boil off into a long tail when they're brought close to the sun. If you've ever seen a comet, you're not likely to forget that sight. And the 1990s was a great decade for watching comets. The most recent bright one was comet Hale-Bopp. It reached a maximum brightness in the spring of 1997. The previous year, comet Hyakutake was widely visible. By the way, comet names come from the discoverer. There are many, many amateur comet watchers, and they do regular sky surveys. They look for any fuzzy moving objects, so this is an area where a dedicated amateur can actually make a mark in science. You might also remember the dramatic impact of comet Shoemaker-Levy 9 on Jupiter. That was in July of 1994. That comet fragmented, broke up into about 20 pieces, and then hit Jupiter in a series of giant impacts. Now, comets tend to have extremely elongated elliptical orbit. Those orbits often extend very, very far beyond the outer planets. Many comets, in fact, take tens of thousands of years to complete one trip around the sun. Other comets, like the renowned Halley's Comet, have much shorter periods with orbits of tens or hundreds of years. Comets are thought to originate in what's known as the Oort cloud, which is a relatively, it's a distant band of relatively small objects that lies far beyond the outermost planet Pluto. And the comets we see are thought to be somehow knocked out of their more distant orbits. Beyond Pluto also lies the mysterious Kuiper belt, which has a large number of enigmatic objects in orbit. What little we can tell about these masses comes from reflectance spectroscopy, and these spectra suggest that the Kuiper belt objects may be a combination of comet-like ices and asteroid-like rocks. Well, that's a pretty considerable inventory. While most of our knowledge about the solar system comes from remote observations with telescopes and occasional space probe missions, scientists have also been able to study actual samples from space. And first and foremost are the meteorites, which are extremely important in this regard. A meteorite is nothing more than a rock that falls to Earth from space. Now, these rocks fall on every part of the Earth's surface. The most obvious ones are exotic-looking irons. These are actual chunks of iron with rather pock-marked and contorted shapes. It's likely that they provided metal for some of the earliest metal implements, but there are also stony meteorites and mixed metal and stone meteorites. Of special interest are thousands of pristine meteorites that have been found in recent years on the surface of ancient ice fields in Antarctica. Now, this is a really neat discovery. There are, in effect, ice deserts in Antarctica where virtually no precipitation occurs for thousands of years. So these fields of ice offer a flat, white surface on which meteorites simply fall and accumulate. So scientists glide across the ice in snowmobiles or they fly in helicopters, and they find scads of meteorites just lying about. Now, these Antarctic meteorites are tremendously important because they represent a truly random sample of rocks from space. You see, in ordinary land areas, stony meteorites often just look like a rock that you'd kick out of the way. So the vast majority of finds are irons on land. But the Antarctic sample reveals that stones are much, much more common than irons. By the way, lots of meteorites are now coming out of the Sahara Desert for exactly the same reason. The desert is a perfect environment to accumulate rocks from space. Only most of these meteorites go to the collector market without any documentation or handling. This is really big business for the nomads in the desert. Some individual fist-sized meteorites can be worth more than $1 million. Well, here's another intriguing wrinkle. While the vast majority of meteorites appear to be fragments of asteroids, a small number, perhaps only a dozen in all, bear strong evidence that they were blasted off the surface of Mars. These meteorites, they have small gas bubbles trapped in glass, and the composition of that gas is identical to the very distinctive composition of the Mars atmosphere. So how can that possibly happen? Well, it turns out that when a large asteroid hits the surface of Mars, lots of material is blasted out, and much of the rock is vaporized, but a small fraction actually gets sort of lifted into space as chunks of rock that don't suffer much damage. Then some of these rocks wind up in Earth-crossing orbits, and they fall from the sky as meteorites. So meteorites provide tantalizing glimpses of Mars, but scientists would really like to collect their own surface rocks. Mars sample return missions are in the planning stage for the second decade of the 21st century. One current idea is to launch a probe, perhaps from the space station to Mars, and then part of the probe will drop down to the Martian surface and pack soil and rocks into a couple of canisters about the size of a Coke can. Then those canisters will be rocketed back into orbit where they'll be recovered remotely and returned to Earth. That complicated process saves a lot of fuel. But however they do it, a Mars sample return will be very, very difficult. Obtaining Mars samples is a tremendously exciting prospect. My laboratory is one of the many places that's actually gearing up now to study those samples in a decade or more. And then we have the moon rocks, samples returned from the moon primarily by the hundreds of kilograms of lunar rocks and soil that were collected by the Apollo astronauts. Those have been instrumental in developing new theories about the moon's origin and evolution. Each of the 6 Apollo missions that touched down on the moon brought back samples. And I especially remember the very first mission in 1969. See, I was at MIT at the time, and my thesis advisor, Dave Wuns, was on the elite sample return team. So the Apollo 11 astronauts, they brought back 21.5 kilograms, that's about 47 pounds of rocks and soil. A lot of people were deeply worried about possible space bugs or other harmful effects, so those samples had to undergo a preliminary quarantine for 50 days. Dave was one of the team of scientists locked into a sealed area where the first studies were made on those rocks. Actually, the moon rocks turned out to be remarkably similar to Earth rocks, so similar, in fact, that it led to a new theory of the moon's formation. More about that in a bit. Well, let me tell you the story. After several weeks, Dave Wuns and the other scientists were let out, and most of them were allowed to take a small amount of the precious sample back to their labs. Well, this transit was done under the watchful eye of armed guards. These moon rocks were immensely valuable. So imagine this. Here comes Dave Wuns back to the 12th floor of MIT's Green Building, that's the Earth Science Building, and he's dwarfed by this big burly guard. He's got a gun in his side, not typical of scientific laboratories, and Dave has to divide his sample of lunar dust into 2 parts so that half of it can go to another scientist. So the guard's standing over Dave, and the rest of us were all there watching his every move, and his hands were shaking. He was so nervous. He was pouring the powder from one vial to another with a piece of powder paper, and he was so nervous that he spilled dust all over his fingers and on the paper. He finally managed to get most of the dust into the vials and tighten the caps, so the guard left with that half sample. But we saved that powder paper, which had Dave Wuns' fingerprints in moon dust, as a rather unusual souvenir of that time. Well, there's one other source of samples from space. The solar system is also rich in what are called interplanetary dust particles, or IDPs. These can be obtained and collected by high-altitude aircraft. These are microscopic fragments. Some of them are burned up ash from meteors that come in. Some are actually primordial dust that never found its way into the sun or a planet. Now, it's amazing how these things are collected. NASA got a hold of an old U-2 spy plane. They send the plane up to extremely high altitude and sort of sweep a section of sky to collect dust. Now, while most IDPs represent debris from the process in our solar system, a small fraction is material that apparently have been drifting in space since long before our solar system formed. So these are rare, odd particles that have bizarre isotopic compositions that could only have come from earlier generations of red giant stars or supernovas. These microscopic pieces of distant stars are providing astrophysicists with a treasure trove of data. Those data constrain models of star formation and evolution of planetary systems as well. So that's a quick review of solar system objects and our precious hoard of physical samples. Now, let's turn our attention to how the solar system began. Objects in the solar system display a number of distinctive characteristics, and these traits give hints about the origin and subsequent histories. Look at the solar system and consider the very non-uniform distribution of mass. See, almost all the mass of the solar system is contained in the sun. It's roughly 1,000 times more massive than all the planets combined. The sun actually has 99.9% of the mass of the solar system. Then comes Jupiter, the largest planet, which is more than twice as massive as all the other planets combined. All the Jovian planets are much more massive than the terrestrial planets. Jupiter, for example, is about 320 times more massive than Earth. So the Earth and the other terrestrial planets account for much less than 1,000% of the mass in our solar system. That's a pretty skewed distribution of mass. And then second, think about orbits in the solar system. Even though the sun is the most massive object in the solar system, more than 99% of the orbital kinetic energy, the circular motion of the solar system, is in the Jovian planets. The massive gas giant planets hold almost all of the angular momentum. Think about the similarities of orbits shown here. All planets orbit in almost exactly the same plane, which is defined in space by the 12 constellations of the zodiac. The zodiac is a band of stars near the equator. All the planets, the moon, and the sun, not to mention most asteroids and comets, lie in that band. All planets orbit in the same direction around the sun. Looking down on the northern hemisphere of Earth, orbits are all counterclockwise. The direction of the orbits is the same as the direction of rotation of the sun and of most of the planets, furthermore. That is, looking down on Earth, again, almost all the planets rotate about their axes counterclockwise, with their axes more or less perpendicular to the plane of the zodiac. This uniformity is surprising in one sense. See, according to Newton's laws of motion and Kepler's laws of orbits, the planetary orbits could be in any plane at all with any rotational sense. The 9 planets could be going any which way, but they don't. That uniformity of motion points to some aspect of the origin of the solar system. Scientists also learned about the solar system's history from the age of its matter. Moon rocks display a variety of ages from almost 4.6 to about 3.2 billion years. Many meteorites also show a 4.6 billion year age. These ages suggest that much of the solid material in the solar system first crystallized at about 4.6 billion years. From this data, the age of the solar system is estimated to be slightly more than 4.6 billion years. Now, taking all this data into account, the generally accepted model for the formation of stars, including the solar system, is called the nebular hypothesis. This theory was proposed by Pierre-Simon Laplace, who was born in Normandy, France in 1749. Now, Laplace was a brilliant mathematical prodigy. He actually became a university professor at the age of 19. And he described his nebular theory in the extremely popular work, Exposition of the System of the World. That was published in 1796. On his deathbed in 1827, Laplace expressed sentiments shared by most scientists, even if they're rarely spoken. He said, "The knowledge we have of things is small indeed, while that of which we are ignorant is immense." That is a great deathbed quote for a scientist. Now, according to his nebular hypothesis, a solar system begins as a giant cloud of dust and gas like this. Gravity gradually attracts this dust and gas into an ever denser and more compact cloud. This process of compaction, once started, will accelerate as the mass becomes more compact and the force of gravity becomes more efficient. The composition of the nebula will be primarily hydrogen, with various other elements depending on how many generations of supernovas contributed heavy elements to the cloud. Later generations of stars have more of those heavier elements. Our solar system, which is about 90% hydrogen, may have been preceded by half a dozen or more cycles of exploding stars. Now, throughout this process, the temperature of the collapsing cloud has to gradually increase as the gravitational potential energy is converted to heat. The cloud probably starts off with irregular swirlings, but as the mass falls to the center, the cloud begins to rotate faster and faster, like a skater who pulls in her arms during a spin. Now, eventually, the solar system looked like a rotating disk of matter here, with a large bulge at the center. This stage of solar system formation is not unlike a spiral galaxy in its general outlines. Now, most of the mass of the solar nebula got pulled to the center, where the protosun got hotter and hotter. Pressures inside this hydrogen sphere also increased as the central mass got larger. At some critical point, the nuclear fires inside the sun ignited, and our star was born. It took some tens of thousands of years for that nuclear energy to work its way outward to the sun's surface. But when it did, a strong solar wind began to push outward from the sun through the rest of the solar system. The heat and wind from the sun stripped the inner planets of most of their hydrogen, helium, the other volatiles. That process left behind the 4 rocky terrestrial planets. Much farther out, it was cool enough for hydrogen and helium to condense into the 4 Jovian planets. Lots of astronomers have wondered how likely it is to form a solar system like ours elsewhere in our Milky Way galaxy. Is the nebular model true for most or even all stars, or is the solar system a very special case? Now, one way of tackling this question is to devise computer models that keep track of the evolution of a dust cloud under gravity. One surprise is that under most conditions, you don't get one star. In most simulations, 2 stars wind up forming a binary star system. This is a consequence of the amount of initial angular momentum. Faster rotating clouds tend to spread out the mass into 2 lumps. And this theory is borne out by observations too. More than 2/3 of all nearby stars turn out to be part of binary systems. You know, it's intriguing to think about the solar system in exactly that context. If Jupiter had been about 50 to 100 times larger, we'd also be in a binary star system. Jupiter is just a little bit too small to be a star. When only one star dominates a system, calculations show that a pattern of planets like our own is quite probable. Astronomer George Wetherell of the Carnegie Institution of Washington has made hundreds of calculations like this one. Wetherell begins his calculation by putting tens of thousands of 10 to 100 kilometer sized planetesimals in orbit around a sun-like star. Then he just lets them all go and sees how they clump up. Almost always he finds 6 to 10 planets more or less regularly spaced arising out of the chaos. This process is also relatively speedy. It takes place in just a few thousands of years. One fascinating aspect of these calculations is the importance of late-stage collisions in fixing the details of planetary behavior. Near the end of the process, several very large objects, perhaps the size of Mars, can share similar orbits. Now, such a situation is inherently unstable, and it eventually results in an epic collision in space. Such collisions may be the cause for some of the anomalous behavior of planets around our sun. For example, Venus actually rotates the wrong way compared to the other planets. This so-called retrograde rotation of Venus might have resulted from a late collision. Similarly, the rotation axis of Uranus is tilted sideways, and this could also have been caused by a collision as well. So is there any observational evidence that planetary systems form around other stars? Could there be other planetary systems? After all, if solar systems form from contracting disks of gas and dust, then there must be many such objects in our own Milky Way galaxy today. In fact, the Hubble Space Telescope has produced a number of dramatic images of what are believed to be dynamic star-forming regions in nearby space. Just look at this image. Immense dust concentrations with dramatic fingers of matter are seen in the Eagle Nebula. The Hubble Space Telescope has also captured what appear to be stars surrounded by disks of dust. These objects may be solar systems in their first million years of formation. Well, I want to end by telling you the amazing story of the moon's formation, at least the current version of the story. This model of the origin of the moon illustrates the dynamic nature of planet-forming processes, and I have to admit it also is subject to change in case new data comes in. Well, the moon is an oddity. It's one of the solar system's more enigmatic objects. It's the only large moon of a terrestrial planet. For one thing, it's only slightly smaller than the planet Mercury. And its age is quite similar to that of the Earth. And most curiously, the composition of the moon is very similar to that of the Earth's mantle. That's the bulk of the Earth's interior, taking away the core, which is metal, or the crust, which has lots of light elements. And how can that be? As we'll see in Lecture 37, the Earth differentiated early in its history. The crust, the mantle, the core are chemically very different. So how can the moon be so similar just to the mantle part of the Earth? Well, let's go back to the solar nebula. As the nebular disk is flattened, small bits of matter begin to clump together, forming ever larger masses. Larger clumps exerted proportionally larger force on surrounding matter and thus grew at the expense of smaller fragments. The growing proto-Earth and other planets acted like great vacuum cleaners in space, sweeping up mass in the vicinity of the present Earth's orbit. What happened? Eventually, two large objects competed for Earth's orbit. One was slightly smaller than the present Earth, and the other was quite a bit smaller, probably about the size of Mars. Well, here's what happened. According to current models, about 4.5 billion years ago, these two planet-like objects collided in what must have been an awesome event. Computer simulations suggest that the two objects were partially disintegrated and merged together, while a huge chunk of Earth's interior, its mantle, was blasted out into orbit to form the moon. That's why the moon has a composition that's so similar to the Earth's mantle. It actually is a piece of Earth's mantle. The surfaces of both the moon and the Earth were molten at that point. That's about 4.6 billion years ago. That's when all the radioactive clocks were set. Now, this is admittedly an amazing story, but as we'll continue to see, the solar system is an absolutely amazing place. So in summary, the solar system contains all the objects that are gravitationally bound to the sun. That's 9 planets, lots of moons, their rings, countless comets and asteroids, and more. According to the nebular hypothesis of Laplace, these objects formed from a great cloud of dust and gas more than 4.5 billion years ago. The sun got most of the mass and became a star. The planets got most of the angular momentum and they orbit the sun. The 4 inner terrestrial planets were subjected to the sun's intense heat and solar wind, and their relatively small rocky worlds The more distant gas giants were a lot cooler, so gases could condense. These big planets are giant balls of hydrogen which aren't quite large enough to become stars. So that's an overview of the solar system and its formation. And in the next lecture, we'll take a closer look at the individual